This is General Physics 2, Week 10 on AC. This is lecture parts 7 and 8. This is going to be. Let's see if I can switch over. And you should all now be seeing this screen over here. So I'm going to talk about transformers. They are the magical answer to the question that I posed in the last video. That was part 6. Ignore the 4 up here. This is part 7 and 8. Transformers. You saw these in lab. You put them together a couple different ways, and you hooked up a power supply here that was plugged into the wall, but it was outputting AC. So you were feeding an AC waveform into the transformer, and then looking at the AC waveform at the output of the transformer, and then you connected it up with a light bulb and switched it on and off and did various things like that. And you also rearranged the transformer. The crucial thing in a transformer is the turns ratio. How many turns, how many coils do you have in the secondary, and how many are there in the primary? So first, let me just try to describe a little bit how these things work. It is a tricky business. It's not a simple thing to understand, but finally, the answers, the way you actually use them and the formulas that you use are extremely simple. So when you have an AC waveform hooked up to something like this, then current will flow in these coils, and that current will go back and forth as the current alternates, as the applied voltage alternates. That generates a B field that is alternating as well. It's going through here. And the B field lines would go right through both coils. They tend to follow through the magnetic material, the iron of the core, we call this. And so the lines that are generated in this, the B field lines here, all go through the second one. So these B field lines that are changing because the current is changing. The current is going one way, and then it's changing and going the other. The B field lines go one way, and then they turn around and go the other way. So the B field is growing and then shrinking and growing in the other direction. And that, of course, means you've got a changing B field through this other coil, and that induces an EMF in the second coil. So that gives you an idea of why you would have an alternating voltage coming out on this side, and perhaps even explains why nothing happens if you have DC. You apply DC on here and you don't get anything at the output. It's only when you first apply it or when you take it away that you get something at the output. What's tricky to understand is why the EMF at the output depends on the ratio of these turns. You might think it would be the product or something like that it seems like putting more coils on either side would give you a stronger EMF here, but it's not true. And the reason is because of a strange effect here called a back EMF. The changing B field in this first coil actually induces in it an EMF. That's the weird part. So if you apply an EMF to this, that would tend to make current just start to flow, and that changing current creates a changing magnetic field, and that changing magnetic field, that's a changing flux, creates an EMF back in this very same coil. That back EMF, it turns out if you don't connect anything out here, then essentially what happens is that just the right B field is created in here so that you get a back EMF which exactly matches the EMF you've applied, the voltage that you've applied. You get a back EMF that equals it. So the B field builds up in such a way as to exactly equal this applied voltage with this back EMF. Now perhaps you can see why the turns ratio matters. If that B field is changing in such a way as to create a back EMF here to match this voltage, then if you have all that same B field going through the second set, this second coil. And let's say in the second coil you have twice as many turns. Then you're going to get an EMF in this coil as well. And this coil will have twice the EMF because it's got twice as many turns. So that's where the turns ratio comes in. And that's basically how a transformer works. When you connect it up to some alternating current, alternating power supply, an alternating voltage like this, then what you get at the output is another alternating voltage. And this voltage can be higher, lower, or the same, all depending just on the ratio of turns here. And I've expressed it down here. That's one way of writing it, that the voltage in the primary divided by the turns in the primary equals the voltage in the secondary divided by the turns in the secondary. So if you have twice as many turns in the secondary, then you have twice the voltage so that you still get the same ratio there. So this, what is drawn here, looks like twice as many turns at the output, so that would be a step-up transformer. So if you feed in 12 volts AC, you'll get out 24 volts AC. You could, of course, flip this around and make it a step-down transformer, and then you'd get out half the voltage that was coming in. And of course, we've already talked about the fact that this does not work for DC. Now, I won't try to prove it, but current works exactly the opposite way. When you do connect something up, like a light bulb in here, complicated interactions happen in here, and you end up drawing current from the source. In a disconnected example, very little current actually ends up flowing through here. But when you do connect something here, then current will start to flow in both primary and secondary. And the interesting thing is that the way the voltage, perhaps as shown here, would be stepped up, the current would be stepped down by exactly the same ratio. So if the voltage is doubled, then the current would be half. That is, the secondary current would be half what the primary current was if the secondary voltage is twice what the primary voltage is, because the turns in the secondary are twice what the turns are in the primary. That results when you take current times voltage in the power being the same. The input power and the output power are the same. So over here you might have 12 volts coming in and 1 amp of current, and out here you've got 24 volts coming out and only half an amp of current. In either case, it's 12 watts. That's assuming the transformer is 100% efficient. Real transformers, in many cases, can get close to that. They might be 90% or something, but they probably aren't perfect. Now back to an earlier question. How does this solve the problem with providing power, and why was Edison so badly wrong? Well, this allows us now to use transformers to change the voltage level. And this is what's done in a power distribution system. At the generator, there's a great big step-up transformer that steps the voltage up to some huge number, like 600,000 volts or something like that. And that is the voltage level that you get going across the country. On the lines, such as the lines that went right through campus that we saw them replacing with the helicopters and such some weeks ago, those are carrying some horrendously high voltage and then still just a modest current. It might be several hundred amps, perhaps as much as 1,000, but not much more than that, in a very big, heavy cable. But that then, because the voltage is so high, is providing a great deal of power and can, in fact, supply a large city. Then as you approach that city, somewhere near the outskirts, you have a substation, and there's a great big step-down transformer. And from that, the output, this doesn't show, there are usually more steps than just this many, but it's stepped down to a smaller voltage and spread out to a whole bunch of different wires. So there might be 10 different distribution lines running at this level. And then you step things further down near your house. There's a can out on the pole, looks like a great big can sitting up there, and that's the transformer. And that steps it down to 120 volts. That's safe in your house. So it's all because of transformers that AC has a huge advantage. DC doesn't have transform. You can't use transformers to change the voltage. And so it's much more difficult to use. Here are just a couple of other quick examples. In your car, the way the spark plugs work, the car battery is only 12 volts. That's not enough to make much of a spark. And so there's a transformer. It's called the coil, but it really is a transformer. And it's a transformer that's a very large ratio. The output is, the turns ratio is something huge, so that 12 volts coming in generates something enormous coming out. And the way it's wired up, there's a switch, and it used to be a physical switch. Now it's an electronic switch. It used to be called the points. And this would connect and allow current to flow through this coil. And so here's the current for a certain period of time, and then the switch opens and the current drops to 0. That means that the B field generated in this coil would be some value, and of course then there'd be that much flux, and all that flux goes through the other one as well. And then suddenly that flux disappears. That flux goes from some high value down to nothing very quickly. That change in flux induces an EMF in this output coil that's very, very large. And that's the spike that I'm showing here. And when that spike happens, then there's a distributor that points to whichever one of these. It selects one of the spark plugs and connects up to that. And this is such a high voltage that it creates a spark right in the cylinder and ignites the fuel when it's done at just the right time. This is just talking about another weird effect. If you in motors have windings in them, and those windings actually have a certain well, you know what? I'm going to skip this part. I think we'll just skip this and not try to talk about this. It deals with self-EMF, but it doesn't need to be talked about. So we'll stop there. If I can figure out how to stop.